Multivariable Calculus, Section 12.3, Limits and Continuity. Recall that back in 2 dimensions we looked at limits this way. If L was in fact the limit of an expression in x, that meant that the y values would be very close to L, within epsilon of L, where epsilon could be any small number, whenever x was close to a. And so to prove the limit, we had to find an interval around a, so that if x were within a plus delta and a minus delta, those x values would correspond to y values up near L, within epsilon of L. And so Cauchy's definition of a limit went something like this. Given any epsilon greater than 0, if there exists a delta greater than 0, such that the distance between x and a less than delta causes the distance between f of x and L, in other words y and L, to be less than epsilon, then we say that the limit as x approaches a of f of x is L. And notice that Cauchy used absolute value to indicate distance. The absolute value of x minus a is the distance between x and a, and the absolute value of f of x minus L is the distance between L and y. Now in 3 dimensions it's very, very similar. But this time we want to show that the function values are near the L value on the z-axis. Whenever xy, the point in the xy plane, which is the domain of these 3-dimensional graphs, we want to show that z is within epsilon of L whenever the point is within delta of AB. So instead of finding an interval around A, we have to find a circular region around AB with a very small radius, such that if xy is within that circle, all the corresponding z values will be within epsilon of L on the z-axis. So the Cauchy definition goes something like this in 3 dimensions. Given any epsilon greater than 0, if there exists a delta greater than 0, such that xy being within delta of AB causes the distance between the z value and L to be less than epsilon, then we say that the limit as xy approaches AB of f of xy is L. So if we look at this definition again in 3 dimensions, what we're going to do is we're going to look at the circle again, and basically we have a circle of radius delta centered at AB, and we are to show that if xy is within that circle, the z value will be within epsilon of L. So we use the equation of the circle, and we want that equation contains all the interior points x, y inside the circle, but not the center itself. And then if we solve for delta, we get this expression. So what we're going to do is we're going to replace the English statement, or the English expression there that I've underlined in red, with this mathematical expression that says the same thing. So now we have, given any epsilon greater than 0, if there exists a delta greater than 0 such that xy is close to AB, how close? Delta close. If that causes the function value, the z value, to be within epsilon of L, then we say that the limit as xy approaches AB of f of xy is L. And so we've just replaced some English phrasing with a mathematical expression. Now, don't worry too much about this definition. We're not going to be writing any proofs. This is just a review of what a limit is. You will be using other techniques to evaluate limits. Continuity in 2 dimensions. Recall that if the limit as x approached a of f of x was equal to the function value at a, then we said that f of x is continuous at x equal a. In other words, if that in fact is the limit L as x approaches a, and the function is continuous, then there can't be a hole there, and so the function value, the point, has to plug up the hole and make the function continuous. So in 3 dimensions it's basically the same idea, except instead of a curve with a hole in it, we might have a surface with a hole in it, and that would be a discontinuity. However, if the limit as xy approaches AB of f of xy is equal to the function value at AB, then we say that f of xy is continuous at xy equal AB. So in other words, we have to plug the hole in the surface. And then if there are no holes or any gaps in the surface, we have a continuous function. described by the graph. Number 6. Evaluate the limit as xy approaches 2, 3 of this expression. Now, unless there's an issue with a 0 in the denominator or negatives under the square root or anything that would be undefined as we approach, we can just think of it this way, the same way as we always have. If x gets close to 2, then the numerator is going to get close to a certain number. If x gets close to 2 and y gets close to 3, then we're going to have a certain number in the denominator without any issues. And so it looks like we're just plugging the numbers in, but we're really examining what happens very, very close to those numbers to make sure there's no issues with negatives under square roots or anything like that. So a lot of these are just evaluated by inspection. You just look at it and figure it out. Number 10, the limit as xy approaches 0, 0 of cosine of x squared plus y squared over 1 minus x squared minus y squared. There are no issues here, and so the answer is just the cosine of 0 over 1, which reduces to 1. Number 16, the limit as xy approaches 1 comma negative 1 of the arc sine of xy over the square root of x squared plus y squared. And again, there really is no issue. There are no issues here. The numerator of the fraction approaches negative 1 and the denominator approaches the square root of 2. And the arc sine of negative 1 over root 2 is negative pi over 4. Number 20, f of xy equals x squared y cubed minus 10. And the instructions want you to evaluate this limit and this limit. Now, these expressions should kind of ring a bell. I think you can tell what they are a precursor of. In the next few sections, we're going to be looking at derivatives in 3 dimensions. Just a heads up, the first one here with the h going to 0, that's called a partial derivative for x, and the one on the right there is a partial derivative for y, but we'll get into that later. For now, we're just filling in these expressions and evaluating. So let's look at the first one. F of x plus h comma y means you replace x in the original expression with x plus h, and then you simplify it. So the 10s cancel, and then we can multiply out the square, and then we can distribute the y cubed, and then the x squared y cubeds cancel, and now we can divide by h, and that gives us 2xy cubed plus hy cubed, and since h goes to 0, the second term goes to 0, and we're left with 2xy cubed. And the second half of this problem is similar, except this time you replace the y value, or values if there's more than one, with a y plus k, and then the 10s cancel again, and we can cube out the y plus k cubed using Pascal's triangle, so we can do it quickly. And then instead of multiplying it all out, I think you can see that the x squared y cubed is going to cancel, and now I'll multiply it out, distributing the x squared, and every term has a k in it, so we'll divide by k. And after we do that, we can let any terms with k go to 0, and therefore the answer to this half of the problem is 3x squared y squared. Number 22. Find the limit as xy approaches 2 comma negative 2 of this expression. Well, here we have a slight problem. The numerator is not an issue because it approaches 8. But the denominator is an issue. It approaches 0. Now, the limit maybe could be infinite. So to figure that out, we have to look at approaching x and y from different angles. But if we just consider one of them, if we approach the negative value, the y value, which is causing the problem, from the right, then the denominator is 0 plus. Or if we approach the y value from the left, then we get 0 minus. So we're getting two different answers from the left and the right on y, and so the limit itself does not exist. Number 28. Evaluate the limit as xy approaches 0, 0 of the sine of the log of 1 plus x plus y, and in this case there's no issues, so we can just let x and y both go to 0, and we get the sine of the log of 1, which is the sine of 0, which is 0. Number 30. Evaluate the limit as xy approaches 0, 0 of arctangent of negative 1 over x squared plus y squared. Okay, now we do have a little problem in the denominator. However, as x and y approach 0, even if they approach from the left or the right, you're always going to end up with 0 plus in the denominator. So that fraction is going to approach negative infinity. And if you look at a picture, a graph of the arctangent, as x approaches, or rather as the value of arctangent approaches negative infinity, the arctangent approaches that bottom asymptote, which is at negative pi over 2. Number 34, find the largest domain on which f of xy equal log of 2x minus y is continuous. Well, in order for this function to be continuous, we need 2x minus y to be greater than 0. So if we solve for y, we get y is less than 2x. And so the domain, the subset of the xy plane that we would want to use is the half plane underneath the line y equal 2x. Number 40, solve the limit by converting to cylindrical coordinates. Okay, so we don't have a L'Hopital's rule in our multivariable, but we do have some other tricks. And this is one of them. So here's the limit, and x and y are both approaching 0. Now, if we look at a picture of that, if there's a point for which x and y are both approaching 0, then that means r is also approaching 0. So we can change x squared plus y squared into r squared. And now we've converted our limit into a regular limit with r approaching 0. And this is a limit you really should know by heart, but if not, since we've changed it into just a regular limit with one variable, we can use L'Hopital's rule because both the numerator and denominator are approaching 0. So we can take the derivative of the numerator, which is cosine r, and the derivative of the denominator, which is just 1, and cosine of 0 is 1, and so our answer is 1. Number 44, evaluate the limit as xy approaches 0, 0 of this expression. Okay, so the issue here is both the numerator and denominator are approaching 0, and we don't have a L'Hopital's rule for 3 dimensions. So we need another trick, and what the book's hint is to let y equal mx. So we replace y with mx, and that gives us a single variable limit. Now we can factor out our x to the 4th, and we can cancel it. But now we have an expression in m, and x is the one that's varying. So what we're going to do is just look at 3 possibilities. So I just picked 3 values for m at random, or more or less. And let's see what happens. So if m is 1, then that means z is going to approach 1 minus 1 to the 4th over 1 plus 1 plus 1, which is 0. If m is 0, then z is going to approach 1 minus 0 over 1 plus 0 plus 0, and that's 1. And furthermore, if m is negative 2, then z is going to approach 1 minus negative 2 to the 4th, which is 16, over 1 plus m squared, which is 4 plus m to the 4th, which is 16, and we get this crazy negative 15/21. So depending on the way that y is approaching 0 with respect to x, we're getting different values for the limit. And therefore, the answer to this problem is the limit does not exist. Number 46, show that the following limit does not exist. Limit as x, y, z approaches 0, 0, 0 of this expression. So let's take a look at what happens if x and y go to 0. Then we get the following limit in z. And if we evaluate that, we get negative 1. On the other hand, if y and z go to 0, we get this limit in x, and that goes to 1. And therefore, since we got 2 different answers depending on how the points are, approaching 0, 0, 0, 0 in 3 space, since we got different values, this limit does not exist. This math is so easy, it's so sweet. Have fun with the problems.